Over the past few decades, computational science has emerged as a field that firmly complements the traditional theoretical and experimental pillars of science. In civil engineering, and more particularly in structural mechanics, computational tools are used to understand and predict the behavior of complex structures. These include skyscrapers, bridges, and nuclear power plants. A major complexity lies in the fact that many structures, if not all, are in direct contact with the soil. The dynamic interaction between the structures and the soil often plays a crucial role and should be accounted for in numerical models. An efficient solution to dynamic soil-structure interaction problems is indispensable. For example, for the assessment of damage to structures caused by earthquakes, the evaluation of annoyance in the built environment due to vibrations originated from road and railway traffic, or the design of offshore structures, such as wind turbines, oil, and gas platforms subjected to wind and wave loadings. These problems are of large societal and economic importance. Although substantial progress has been made in recent years regarding the development of efficient prediction models, the numerical solution of large three-dimensional dynamic soil structure interaction problems remains very challenging and in many cases beyond current computer capabilities. In his PhD thesis, Pieter Coulier has developed fast, stable, and accurate numerical techniques in order to cope with ever larger and more complex dynamic soil structure interaction problems.
A state-of-the-art numerical technique for solving dynamic soil structure interaction problems is a coupled finite element boundary element methodology, where finite elements for the structure are coupled to boundary elements for the soil. This approach offers a large modeling flexibility, but unfortunately at a very high computational cost, especially for three-dimensional problems. This is mainly due to the dense matrices arising from the boundary element method, which lead to a quadratic growth of the required memory when the problem size is increased, while the computation time even increases in a cubic way. Within the frame of my PhD thesis, I have developed a fast boundary element method based on so-called hierarchical matrices. When using this type of matrices, the interaction between elements that are far enough from each other are replaced by low-rank approximations, which is computationally very efficient. The near-field interactions, at the other hand, are computed exactly, hence maintaining the accuracy of the method. The application of this new type of matrices results in a significant reduction of the required memory as well as of the computation time, and enables us to solve much larger problems than before with the same computational resources.
Apart from speeding up the boundary element calculations, Pieter has also developed techniques for a more efficient coupling of finite and boundary elements. He has focused on iterative coupling algorithms, in which the governing equations are solved separately for each subdomain, while the displacements and stresses at the soil structure interface are updated until convergence is achieved. These iterative algorithms are significantly more efficient than classical coupling approaches.
The developed methodologies provide an efficient solution to large three-dimensional dynamic soil structure interaction problems. Nevertheless, such calculations still require high-performance computing facilities, and the computation times remain relatively high from an engineering point of view, certainly for structures with large dimensions. In order to achieve a substantial reduction of the computational effort, simplifying assumptions are therefore often introduced in numerical models.
In many cases, the structure is assumed to be infinitely long with an invariant geometry in the longitudinal direction. Such an assumption seems to be valid for roads, railway tracks, tunnels, vibration isolation screens, pipelines, and more. This allows for the use of a so-called 2.5-dimensional approach, in which the longitudinal coordinate is transformed from the spatial domain to the wave number domain. As a result, only a 2-dimensional discretization of the cross-section is required, hence providing a computationally efficient alternative to full 3D computations. This 2.5-dimensional approach is state-of-the-art and is employed by researchers worldwide.
2.5-dimensional formulations are very efficient, but they are limited to structures that are infinitely long, which is in practice of course not always the case. Inspired by developments within the field of vibroacoustics, we've proposed a technique that allows us to account for the finite length of a structure and thus its full 3-dimensional geometry while still using a 2.5-dimensional approach. This technique, called spatial windowing, involves a convolution operation in the wave number domain that is very accurate and at the same time very efficient. As a result, we are able to solve full 3-dimensional dynamic soil structure interaction problems while maintaining the computational efficiency of a 2.5-dimensional approach.
Pieter has subsequently employed his innovative numerical techniques for the efficient solution of several challenging problems related to the prediction of railway-induced ground vibrations. These vibrations are generated at the wheel-rail interface, propagate as elastic waves through the soil, and excite surrounding buildings, where they may cause disturbance to sensitive equipment, annoyance to people, and even structural damage. Increasing public sensitivity to noise and vibration calls for efficient vibration mitigation measures. The high cost of such interventions requires the use of state-of-the-art numerical prediction models.
For existing railway tracks, the most efficient strategy is to intervene on the propagation path between the source of vibrations, being the railway tracks, and the receivers, being the residents of nearby buildings. The main advantage is that no modifications to the track are required, while multiple buildings can be protected simultaneously from vibration.
Typical examples of vibration mitigation measures on the transmission path are open trenches and soft wave barriers, which aim at reflecting the incident waves in order to reduce vibrations behind the barrier. In his thesis, Pieter has focused on an unconventional type of barrier, which consists of material that is significantly stiffer than the surrounding soil. He has demonstrated that such stiff barriers behave fundamentally different, as they do not reflect but block the incident wave field.
A stiff wave barrier can be a very efficient vibration countermeasure, provided that the stiffness contrast between the barrier and the soil is sufficiently large. At very low frequencies, the barrier is unable to impede the propagation of railway waves in the soil, because their wavelength is too large. But from a specific critical frequency on, there are waves in the soil which have a trace wavelength which is smaller than the free bending wavelength of the barrier, and the propagation of these waves is impeded by the barrier because of its large bending stiffness. This is mainly the case for waves that impinge at an oblique angle on the barrier. Waves impinging perpendicular on the barrier still propagate unhindered through it because the wavelength as observed by the barrier is still too large. This results in the existence of a critical angle behind the barrier, which delimits the area where vibration levels are strongly reduced.
This fundamental insight into the behavior of stiff wave barriers allows formulating simple rules of thumb for the critical frequency and critical angle. These rules of thumb can be applied by engineers to assess the expected vibration reduction efficiency of a barrier without the need to perform extensive calculations. Although numerical simulations are indispensable for understanding and designing efficient wave barriers, there remains a strong need to validate these simulations by means of experimental tests. Pieter performed a lab experiment at the University of Cambridge using a large vat of strawberry gelatine to represent the soil, an expanded polystream beam as the wave barrier, and a harmonic shaker as the excitation source. The experimental results revealed that the barrier is very effective in mitigating the transmission of waves, especially at high frequencies. Furthermore, a full-scale field test has been carried out in Spain within the frame of the European project REVIS, where a stiff barrier consisting of overlapping jet grout columns has been installed along a railway track. The measurements show, as predicted, a significant reduction in vibration levels during train passages. Both experiments clearly demonstrate that stiff barriers have a huge potential as efficient countermeasures for railway-induced vibrations. In summary, Pieter has developed multiple numerical tools for the solution of large dynamic soil structure interaction problems. These tools are elegant and fast and are applicable to a variety of engineering problems, such as the design of wave barriers in the soil. The results obtained within the frame of his thesis have been acknowledged as important contributions to the field, as is exemplified by multiple publications in internationally reviewed journals.